All right, so one of the common curves you might have worked with in your math class from your previous math class would be called the bell curve. And that's the same curve we're going to be working with in statistics, but instead of the bell curve, we're just going to call it the normal curve. So there's three reasons why we use this, and one is it has a good description and good descriptions for distributions of real data, such as your SATs. It also has a good approximation. So if we're talking about the coin toss, right? Chances are 50-50, but if you 50-50 getting ahead or the tails, but if you do it enough times, it will, but not necessarily if you do it 100 times. It's close, but if you do it enough times, it will get there eventually. Same thing with the normal distribution. And it's also a basis. So many statistical inferences are based on the normal distribution curve. So when we look at this, when we're creating a normal distribution curve, we see that the mean is in the middle, and then we would have our standard deviation. To the right, we're adding, and to the left, we're subtracting. So each one we're adding is one standard deviation, then standard deviation times 2, and standard deviation times 3, and same thing for the left side. And some properties that we need to look at is that it's also continuous, such as here, there's no discontinuity, as we can see there. It's also symmetric. So from the mean, which is the middle, we can draw a line, and that the left would equal the right. And the median is equal to mode, and nearly all of the distribution, about 99.7%, 99.7% is within three standard deviations. So from here to here would encompass 99.7% of our data. So what about 99.7%? Well, here we can introduce the 68, 95, 99.7% rule. So going through it within our first standard deviation here here would have this side would have our 68% of our data. So from our first standard deviation, both left and right, and of course I'm adding and I'm subtracting, it would this data would have 68% of our data. And then from our second standard deviation, 1, 2, would be 95% of our data. So within the second standard deviation, 95% would encompass that. It also includes 68%. And then ultimately, we would have our 99.7%, right, from within our three standard deviations. So from here to here would encompass 99.7% of our data. So now we get the general aspects. Let's take a look at how we can apply this in real life. So here we're given the test scores for 7th grade students in the middle school in Maryland, and the data is close to normal. And suppose that the distribution is exactly normal, giving us the Q for normal density curve with a mean of 6.84 and a standard deviation of 1.55. So that's all we need, and we are supposed to sketch a normal density curve with the three standard deviation. So the way we could do this is very simple. We draw our x-axis first, and here in the middle would then be our mean, which would be 6.84. Reiterate, this side, the right side is always adding, and left side is always subtracting. So here we're always adding 1.55. Here we're always subtracting 1.55 from our mean right here. So we're supposed to add 1.55. So here would then be 8.39. Second standard deviation would be 9.94. And our third standard deviation would be 11.49. Same thing. First standard deviation subtracting would be 5.29. Second time would be 3.74. And third standard deviation subtracting would be 2.19. As you can see, we've done it. We've sketched the normal density curve on up to 3 standard deviations. So let's build upon that. So next the problem asks for what percent of the scores are less than 3.74. So if we look at 3.74, you'd see that it would be right here. So if we were to count 1, 2, that's our second standard deviation. And same thing, second standard deviation for 9.94. So using the rule mentioned earlier, the empirical rule, which is 68, 95, and 99.7% rule, our second standard deviation, 95% from 3.74 to 9.94. But we're not asked that. We're asked for 3.74 and less. So funny thing about percentages is that when we add this data up, we would see that all of this data would then add up to 100%. So what we can do is using our empirical rule, we can have 100 minus 95, that would be this section right here, would then equal to 5%. The 5%, however, encompasses this part as well as this part, but we're only asked for 3.74 and below. The property of symmetry comes in, and we could divide this by 2, giving us 2.5%. So 2.5% here and 2.5% here, and that's exactly what they were looking for, percent less than 3.74. All right, so let's build upon what we've built up. So again, percent of the scores between this time, between 5.29, which would be right here, and 9.94. So here comes the problem. So if we were to count the standard deviation, it would only be one standard deviation, but this side would have 2 standard deviation. Well, with a little bit of math magic, we're still using our 68, 95, and 99.7% rule, or empirical rule. So just the property of symmetry again. So 5.29 here to 8.39, that's our first standard deviation. So from 5.29 to 8.39 encompasses 68% of our graph. And then our second standard deviation, which would be 9.94 and 3.74, would be 95% of our data. So from here all the way to here, including the 68% right here, would be 95%. Well, knowing that we're only asked for this part, what we could do is we could subtract 95, we could subtract 68 from 95, which would give us 27%. So the 27%, however, does not equal this. 27% would equal this and this. So the property of symmetry applies, and we could divide it into 2, thus giving us 13.5% each. So this side is 13.5% and this side is 13.5, and it'll work because we're only looking for this side. Now, since we have this side, we can then add back our 68% in order to get the percentage of scores between 5.29 to 9.94, and 13.5% plus 68% would then be 81.5%.